All right, so this is lecture 5.1. This is starting chapter 5. Um Chapter 5 and then the next few chapters we start to talk about different applications of group theory. Until chapter 4 we have considered mostly the development of the formalism, and now the first application that we are going to study is the splitting of atomic orbitals in a crystal potential. So this is a very interesting application of group theory and very useful for different technological applications. The idea is to try to study how different degenerate atomic levels in an atom, how they split when the atom, for instance, an impurity atom, is placed in a crystal with a given symmetry. So, and this has important applications in optics, for instance, in the development of lasers, and also in magnetism. It's very important as well. Okay, so we start by considering the Hamiltonian of an impurity ion in a crystal. So this is we write this Hamiltonian from the point of view of perturbation theory in the following manner. We first separate this Hamiltonian in different parts. This first three terms, they correspond to the kinetic energy of the electrons, the Coulomb interaction between the electrons and the nucleus, and this is the electron-electron interaction. So this is the Hamiltonian for the atom. Sorry, for the atom without these other terms, which are also for the atom, the spin-orbit interaction and the hyperfine coupling or the hyperfine interaction. So the point is that these first three terms are typically larger than the spin orbit and the hyperfine interaction, in a sense that sometimes these other terms, they can be treated as perturbation. So this whole Hamiltonian under brackets is the Hamiltonian of an atom, and we also add the crystal potential. This is V crystal, is the crystal potential, which we also will treat as a perturbation to the atomic Hamiltonian. In this approach, then we have two different situations to consider. So the first one is when the spin-orbit interaction is larger than the crystal field, is larger than the crystal potential. So this will be treated in chapter 14, because to deal with this situation we need to consider spin and double groups, something that we're going to see only in chapter 14. Now, what we are going to consider in this chapter is the second situation, so-called the strong field case, in which the crystal field is larger than spin-orbit interaction. So we will disregard these two terms. It's larger also than the hyperfine interaction. So we'll disregard these two terms, and we will consider only the crystal field as a perturbation to this part of the atomic Hamiltonian. Okay. All right. So to do that, we first need to consider some basic results of spherically symmetric potentials, because we have to be able to calculate or to obtain the characters for the full rotation group. So when an atom is isolated from all the other atoms, so it has spherical symmetry. So one needs to this is a type of continuous symmetry that we have not considered yet, and it's not the main focus of this course. but we will need at least to obtain the characters for this so-called full rotation group, which is the symmetry group for a system in which you have full rotation symmetry. Okay? So then we need to remember or to recall a few results regarding spherical harmonics, because if you remember, when you have a central field potential, a spherically symmetric potential, the theta in spherical coordinates, the angular dependence, the theta and phi dependence, are described by these functions, which are the so-called spherical harmonics. I'm not going to review the properties of these functions. All the important properties you're going to find in the textbook, all the important formulas, and also these are also in all basic quantum mechanics books. So what's important for us is not the radial function. This will depend on the specific type of radial potential or atomic potential that we will have. But what's important in group theory is only the angular part, which is described by spherical harmonics. These are solutions for the angular part of the Schrödinger equation of a system in a spherically symmetric condition. So if you know these are the solutions, so then we can use the results that we have obtained in the previous chapter, and we can already understand this angular dependent functions, or is the angular part of the wave functions, as the basis functions for describing the full rotation group, using the results that we described in the previous chapter regarding the relationship between group theory and quantum mechanics. Okay, so and then we already can straight ahead we can understand the degeneracy, or describe to relate the degeneracy of different angular momentum states. For instance, S states, P states, D states. They have a degeneracy of a degeneracy of 1, 3, 5, so on and so forth, corresponding to the different possible values of the quantum number m. And so we can already understand that the full rotation group will have representations of different dimensionalities, 1D representations, 3D, 5D representations, and they will be related. The basis functions for those representations, they will be precisely the spherical harmonics that we are introducing now. Okay? So this is an important result, because this paves the way for us to find the matrix representations, for the irreducible representations, the matrices for the irreducible representations of the full rotation group. You basically can use all the tools that we developed in the previous chapter and use those in this specific case. So the idea is then to remember what we did in chapter 4. For instance, if we go back and look to the equation 4.1, equation 4.1 described the result of the application of a certain symmetry operation, P of R, applied to a certain basis function, as resulting into a combination of all other partners, of all other basis functions that are, let's say, degenerate for that specific representation gamma n. And the coefficients of these expansions are precisely the matrix elements for the matrix representation, the matrix elements of the irreducible representation. Okay? So if you translate equation 4.1 to our specific case now, we know that the basis functions now, they are the spherical harmonics, and basically what this is saying is that when I apply a certain symmetry operation PR of the group in a certain, oh sorry, this is not correct in the book. You have to correct that. Oops. This is not prime. This is basic. Is only theta and phi. So when I apply a symmetry operation, for instance, a rotation to a certain spherical harmonics, the result will be a linear combination. Again, similar to what I had here, it will be a linear combination of all other spherical harmonics with the same value of L, because as we have seen here, the L value is related to the different irreducible representations, but with different values of M. So it's a summation of all possible M prime, and these are the matrices that we need to find. D for each L, for each R, M prime M. Okay, so this is basically it's the same equation as this one, but applied to our specific case now. So let's consider to start with a rotation by an arbitrary angle alpha, okay, around the z-axis. So as an example, this could be, for instance, rotating a px orbital around the z-axis for 90 degrees, and this giving a py orbital. It's not a very good example, because px and py are actually linear combinations of m equals to +1 and m equals to -1. But just to give you an idea what I'm talking about, so for a general case, I want to see what is the result of applying a certain rotation for any given axis actually I'm going to place the axis of rotation around the z-axis. I can always do that. And what is the resulting function when I rotate a spherical harmonic? It's easy to see that basically theta, it's unchanged. I don't change theta because the angle theta is the angle with respect to the z-axis, and I have to transform phi to phi minus alpha. You can think about it and you can figure out that this is the case. And this is easy to calculate because if you remember the formula for the spherical harmonics, the phi dependence is simply e to the I m phi. So if I take phi to the phi minus alpha, I simply get a factor of e to the I m alpha, okay, when I do this rotation, and then I recover the same spherical harmonics that I had before. So this is telling me that the matrix is diagonal. The matrix for the irreducible representation is diagonal because it doesn't couple for this specific rotation, right? It does not couple m to m prime, right? So basically it says that the matrix dl alpha m prime m is a delta m prime m times this phase factor e to the I m alpha. All right, so it's easy to write this matrix. This is the matrix because the different values of m, remember that m runs from minus L to L, right? So if you have to remember that m goes from minus L plus 1, etc. until L, 2L plus 1 values of M. So then I can have this matrix will have 2L plus 1 columns and 2L plus 1 rows, and it will be a diagonal matrix, and the matrix elements are simply that, e to the minus IL alpha, e to the different values of M, right? Alright, so this is the matrix representation for a rotation of alpha, and it doesn't matter the angle of rotation, because I mean for a spherically symmetric system, we're trying to find the full rotation group, right? So for a spherically symmetric system, it doesn't matter if I rotate around a z axis or any other axis. When I calculate the character, it should be the same. So let's calculate the character now. So the character, if you remember, is simply the trace of that matrix, right? So we can basically, you have to go ahead and calculate the trace of this matrix, and this is a simple calculation, because it's a geometric progression, right? So the character associated to the angular momentum number L for a rotation of an angle alpha with respect to the z-axis, it will be simply the trace of that matrix that we have just calculated. And you take the formula of the sum of the geometric progression, and it's e to the I L alpha, e to the I alpha, the first term times the ratio, e to minus the last term times the factor minus the first term, which is e to the I minus I L alpha, divided by e to the I alpha minus 1. And I can multiply this to make it more symmetric. I can multiply this by e to the minus I alpha over 2 in the numerator and in the denominator, and the result of that is e to the L plus 1/2 alpha minus e to the minus L plus 1/2 alpha, and in the denominator we have e to the I alpha over 2 minus e to the minus I alpha over 2, and so basically we have sine of L plus 1/2 alpha times alpha divided by the sine of alpha over 2, right? So this is the result. This is the character then for this symmetry operation, rotation about an angle alpha, for any value of alpha. All right? Very good. So how about other symmetry operations? For instance, what is the character for the inversion operation? So let's remember then our spherical coordinate system. If we think about inverting a position of a certain point of a function, so instead of calculating the function at this point, at this point R, I calculate at the point minus R. So it's not very good my drawing here, but this is the minus R. This is a R, some vector R, and so if you forgive my drawing, but if you think about the geometry in this problem, you can see that when I apply the inversion, this is the inversion operator, right? It's not the imaginary number. So when I apply the inversion, you can see that this takes me to the position pi minus theta and pi plus phi. Okay, if you look at this and think about it, you can see that this is the case. And you can look into the properties of spherical harmonics. I'm not going to do this calculation, but I'm just saying to you that this is what you get. When you invert a spherical harmonic YLM, you basically multiply it by minus 1 to the L. Okay, so for L even, let's say for L equals 0, an S state, or L equals 2, D state, basically it's unchanged. So they have inversion symmetry. They are even under inversion. But for L odd, for odd values of L, let's say a P state. So a P state, if you remember, it's a plus and minus, has positive and negative values. You can see that when you invert, you get the same function multiplied by minus 1. So for odd values of L, you basically get the negative of the function when you invert. Okay, so this makes some sense. All right, so these are the characters for the inversion operator. And when you calculate the trace, again, it's very easy to calculate the trace for the inversion. You basically, again, have to sum over all values of m, from m equals to minus L to m equals to L, this quantity, which is a constant, doesn't depend on m, so it's basically 2L plus 1 times minus 1 to the L. All right, so this is the character for the inversion. In principle, I also have to calculate characters for mirror planes like sigma V, sigma H, sigma D, and also characters for improper rotations like Sn. It's a rotation followed by a reflection. So to do that, I actually need to use properties of factor groups that it's a subject of chapter 6. Next chapter we're gonna see that. So I'm going to postpone this calculation or this discussion to the next chapter. This we will see in chapter 6. But we can go ahead and do some examples for groups that do not have those symmetry operation, and this is still going to be useful for us. All right? Okay. So let's do an example. Let's consider the crystal field splitting for a certain transition metal ion, for instance, any transition metal which has D states. The open D shells are interesting to study in this situation. And let's see what happens when I place some impurity atom, like some transition metal atom, in an environment which is essentially a cubic crystal field. So if I place an atom in the center of for instance, in a site in which I have cubic symmetry, this is also known as an octahedral symmetry, because all the first neighbors, they form an octahedral around the impurity atom. And so what we want to do is to see how the different atomic levels split. In particular, for this case, it's interesting to see or to study how the D states split. The D states, which are initially 5-fold degenerate, it's interesting to see how they split when I place them into a cubic environment. So, and again, to make this simpler, I'm going to assume that because the full cubic group is a OH group, because it has all the reflections and inversions and so on and so forth, and to make it simpler, and because we don't know it, still don't know how to calculate the characters for reflections. Let's assume that I have, instead of OH symmetry, let's assume that I have a simpler O symmetry. The O symmetry has only rotation symmetry. It has C4 axis, X, Y, and Z, C4 axis. It has this C2 axis right here that goes from the center of the cube to the center of the edge. And it also has C3 rotations along the main diagonals. Okay, so this is the character table for the O group. Again, I have the identity, 8 C3 axis, 3 C2, which are simply C4 squared. I have the C4 operations, 6 of them. And I also, because I have plus and minus 2 pi over 4, right, around X, Y, and Z. And I have 6 C2 prime rotations. Okay? And this is the tabulated character table for the O group. I list here the different irreducible representations. For this case, I have 2 1D irreducible representation, 1 2D, and 2 3-dimensional irreducible representations. These are notations for the different irreducible representations using 2 different systems. This is a more, let's say, this is the one we have been using so far, is a molecular, it's more common in chemistry, is a molecular notation in which most of the times we're going to see letters A or B for 1D representations, letter E for 2D, and letter T for 3D representations. And this is another notation which is due to Wigner, which is basically another way to write to indicate these different irreducible representations. The book uses both notations. It depends on the particular problem. So you will need to get used to both of them. But most of the time, I think we're going to use this notation. All right? Okay. So the example we're going to do, as I said, is L equals to 2. So we have to use the formulas, this formula that we have developed, the character for different types of rotations, for this specific case of L equals to 2 to understand this problem. So the first step is simply to calculate the characters for the full rotation group for L equals to 2. Okay? So for the different symmetry operations, for instance, for the identity operation, the identity means rotation by an angle of 0, right? So basically I have to take the limit when alpha goes to 0 of the character chi L of alpha, which is the limit when alpha goes to 0 of sine L plus 1/2 alpha divided by sine of alpha over 2. And this limit is basically L plus 1/2 times alpha divided by alpha over 2, which is basically 2L plus 1, right? So 2L plus 1 is the character of the full rotation group for any value of L. In the case of L equals to 2, the character is for the identity is 5, right? Which it's reasonable because it's a dimensionality of the representation. Okay, so let's do some other cases. For instance, let's take, I don't know, C3, the C3, the 8 C3 class, the C3 operation. We have to calculate the character for L equals to 2 of an angle alpha. For the C3, the alpha equals to 2 pi over 3, right? So this is going to be sine of 5/2 times 2 pi over 3 divided by the sine of pi over 3, right? And if you do this calculation, you do the math, this is a sine of 5 pi over 3 divided by the sine of pi over 3. This is a minus 1. It's minus square root 3 over 2 divided by root 3 over 2. This is minus 1. Okay? And you got the idea, right? So you do this for the different angles. I'm not going to do all of them, just 2 of them, just to see, just to show you how it goes. So, and the result is what you see in this line. You see this is L equals to 2. These are the representations for the full rotation group. For L equals to 2, the character is 5 for the identity, then minus 1 for C3. And if you do the same exercise for the C2 rotation, you get 1. So this is 1. This is a C2 rotation. This is also C2 rotation, C2 prime. So this is also 1. And for C4, if you do the same calculation, it's minus 1. So basically what we did was to find the characters for the full rotation group using the formula that we discussed in the previous slide, okay? Very good. And in this table, this is a table from the book. You have this character table for the O group, the character table of the full rotation for all different values of L. L equals to 0, 1, 2, 3, 4, 5, so on and so forth. Okay. So what we want to do now is to see how the different atomic levels split. So what we need to do, let me reproduce again the same table here in the next slide. What we need to do is to see how this L equals to 2 representation of the full rotation group, which is a reducible representation for the O group, how it decomposes into the irreducible representations of the O group. The result is here, right? We're gonna do this calculation, but already in this table it gives you this result. It basically says that this gamma 2, let's call it, I think the book uses another notation different from the table, different from the one it uses in the table. It calls it gamma rotation for full rotation for L equals to 2, so gamma rot 2. it's saying that for this specific case it will decompose into E plus T2. So we have a five-fold degeneracy, or a five-dimensional representation. It will split into a double degenerate state and a triply degenerate state. So we expect that a five-fold D level will split in this case into a doubly degenerate level and a triply degenerate level from what we discussed in the previous chapter. Okay, but let's calculate this. Let's use the decomposition formulas that we learned in the previous chapter. If you remember, we can write the character for a reducible representation for any class as a linear combination of characters for the irreducible representations for the same class. And this integer coefficients A of j are simply obtained using this formula. So we can see how it goes for this specific case. So let's calculate first, let's see, A of A1. Let's see how many times the A1, the identity representation, or gamma 1 if you will, how many times it is contained in the gamma 2 rot representation. So if you apply this formula, so how many symmetry operations I have? I have 24 symmetry operations, right, for this group. So it's 1 over 24. And I apply this formula, so basically I multiply 5 times 1 times 1. So it's 5. Plus minus 1 times 1 times 8. 8 is the number of elements in the class, right? So it's minus 8. And the next one is 3 plus 3. The next one is 1 minus 6. And for C4 I get minus 6, right? No, plus 6 and minus 6. Because this is 1 plus times 1 minus 6. This is plus 6. This is minus 6. And you can see this is equal to 0. So A1 is not, so the gamma 2 does not, A1 is not contained in gamma 2 rot. Okay, let's do A2. So the coefficient A of A2 is equal to 1 over 24. So now I have to multiply by the characters of gamma 2. So it's 5 minus 8. So they're all the same except for the last two ones they change sign, right? So this plus 3, this is minus 6 plus 6. Okay? Because basically these two numbers, they have opposite signs than these other two numbers. So this is also 0. So let's see now E. A of E. 1 over 24. Let's see. 5 times 2 is 10. Minus 1 times minus 1 plus 8. 1 times 2 times 3, 6 plus 6. And the other two are 0. Plus 0 plus 0. Because these two characters are 0. So this is a non-zero case, so basically this is 1. Okay. Now A of T1 is 1 over 24. Let's do it faster now. 15 plus 0 minus 3 minus 6 minus 6, which is 0. And finally T2. 1 divided by 24. 15 plus 0 minus 3 plus 6 plus 6, which is also equal to 1. So as expected, as we have anticipated, we get 1 here, 1 here for representations E and T2. So basically, as a result, we can say that the D states, or the representation gamma 2, it splits under the action of the O symmetry, the crystal field, into the sum of E and T2. Okay? Alright, so as I said before, this means that if I had originally a 5-fold degenerate state, which is a D state, in spherical symmetry, when I have this in an octahedral crystal field with O symmetry, it will split into a 2-fold level of symmetry E and a 3-fold level of symmetry T2. Okay, so this is, you see that this is a very powerful result of group theory. So it tells you exactly how a level will split when I place the atom in a certain environment with a given symmetry. So, but one thing which is important to say, a group theory does not tell you the order of the two different levels. So the way I draw on here is that the 3-fold level, it's lower energy than the 2-fold, but this is just schematic. Okay, so I really don't know which level is going to be lower energy. Group theory does not tell me that. It only tells you how the level will split, the degeneracy of the resulting levels. As we're going to see in the next lecture, we're going to see how one can use some physical concepts and physical ideas and try to guess or to infer which one is going to be the ground state, but it's not group theory that tells you that. Only other types of physical reasoning. Okay? All right, very nice. So let's do one more case. Let's suppose now that we apply strain and the symmetry is reduced a little more to tetragonal symmetry, D4, the D4 group. Okay, so that's the idea. I have an impurity atom right here in the middle, and before I had a cubic environment, and now I apply some stress in the crystal and I break the symmetry so it becomes tetragonal. So it's like the lattice, XY lattice constant is different than the Z lattice constant. So now I have a D4 group. So this is the character table for the D4 group. Of course, it's a much smaller group. It has 1, 2, 3, 4, 5, 6, 7, only 8 symmetry operations instead of the 24 that I had before for the group O. Okay? And let's see how the levels further split when I reduce the symmetry. There are two ways I can do that. So let's start from the representations that I had before from the O group, which I have found in the previous slide. I had found the E two-fold degenerate level and a T2 three-fold degenerate level. And again, we can do this one more step. We can see how these representations, now they are going to be reducible representations for the D4 group. And I can try to see how they decompose into the irreducible representations of the D4 group, which are these 5 possibilities here. Okay? So again, the way to do this is similar to what we did before. It's basically the same type of calculation, but we just need to be careful in constructing this table here. So this is the character table for the O group, right? This is what I had before, and I had these two different symmetry operations, E. I have to focus, oops, sorry. I have to focus on these two different representations, E and T2. Cannot write here, so this is T2. Okay, and these are the characters. So I have to look what symmetry operations that I originally had for the O group, which of them remain for the D4 group, and I have to find the corresponding characters that I have here for E and for T2. And I have to write here in the same columns, let's say, in the same table as the D4 group. So you see the idea, right? So for instance, the identity operation, the identity class. I basically have to go back here and see, oh, this is obvious, but I mean, the identity character is 2 for E2 and 3 for T2. It's 2 for E and 3 for T2. Okay. All right. So let's say now C4, the C4 operation. The C4, when I go from cubic symmetry to the tetragonal symmetry, only one C4 operation remains, which is the C4 rotation about the z-axis, right? But this is precisely the same operation that I have here. This is the C4 operation for. So the only difference is that before I had 6 of them, now I have only 2 of them. I'm looking at the C4 first, okay? But the characters should be the same. For the character for E is 0, and the character for T2 is -1. So that's why I get 0 for E and -1 for T2. Let's see the C2 operation, the C2 which is in the main axis, right? This C2 which is a result of 2 combined C4 operations. So basically this is the same symmetry that I had before. So I have the characters are 2 and -1. So that's why I have 2 and -1 here. Okay? Alright, so now we need to be careful because for the D4 I have 2 types of C2 axis. I have C2 prime, this is C2 prime, and I have C2 double prime, which is this axis. This axis right here. This is the C2 double prime. And they correspond to different operations of the original cubic group. The C2 prime, if you think about it, is basically it's a symmetry operation over one of the main symmetry axes, X, Y, or Z, right? So I have to, for the C2 prime, I have to take the character of corresponding to the 3C2 class of the O group, which is again 2 and -1. So that's why I get 2 and minus 1 here. And for the C2 double prime, this corresponds to the C2 prime symmetry operation of the cubic group, and the characters are 0 and 1, so that's why I get 0 and 1. Okay. All right. So then after you find the characters, the idea is just the same as we did in the previous slide. You decompose these two reducible representations into the irreducible representations of the group. I'm not going to do the calculation because it's very similar to what we have done before. And the result is this. So the E level, the doubly degenerate level, splits into A1 and B1, splits into two non-degenerate states. And the T2 level, triply degenerate, it splits into E plus B2, into a double degenerate and a one non-degenerate state. So that's the diagrams that I have for this case. So this is what I had before. Going from spherical symmetry to the O symmetry, 5-fold level splits into 3-fold T2, 2-fold E. And now if I further reduce the symmetry to D4, tetragonal symmetry, I split even further. I mean, the T2 gets splits into 2-fold and a non-degenerate states, symmetries E and B2. And the doubly degenerate states splits into A1 and B1. So we can start to see here something which is probably already very familiar to you, is that the less number of symmetries that we have, when you have groups with a small number of elements, small number of symmetry operations, the degeneracies get smaller and smaller. You start with a very symmetric situation that allows you to have a 5-fold degenerate level. You reduce it to O symmetry and splits into 3 plus 2. And if you reduce even further, you still start to break even more the degeneracy of the levels. So in the end, if you reduce even further, you're going to see only non-degenerate states. Okay, so that's a basic concept that we see many times in physics, that the degeneracy of eigenstates are related to symmetries of your Hamiltonian, and that's you can see how this comes naturally from group theory and from the analysis of the dimensionality of different representations. Okay. All right, so these are the levels that I get from going from the spherical to O to D4. I could arrive in the same result going straight if I went straight from spherical symmetry to D4, right? Just as I went from spherical to O, I could as well go from spherical to D4 straight without going to O symmetry first. So then it's basically I would start again from the full rotation gamma 2 irreducible representation and decompose now into the irreducible representations of D4, and the result would be essentially the same, right? I have to get the same results: A1 plus B1 plus B2 plus E. So A1 plus B1 plus B2 plus E. So this is, you can check that this is correct if you want. Okay? I think this is all for today. So, thank you. And next, on Wednesday, we continue this chapter 5. Thank you.